Alright, so in this problem we're given a rod with a barbell attached, and on the barbell is attached two balls. Alright? And what we want to do in this problem is find the angular momentum, the rotational, the translational, and the total angular momentum. Alright, so first thing we're going to do is the rotational, and we know that inertia times omega gives us the angular momentum. So our formula for inertia is given right here, and it's the mass times the radius perpendicular squared for each mass. And so we have two masses here, which is each ball. And we know that each ball has the same radius because each one is the same distance from its axis, which is just 1/2 of d. So we could simplify this, and we get 2m times 1/2 d squared. Alright, and if we multiply that entire equation by the omega for the barbell, then that'll give us the rotational angular momentum. So we'll just plug in those numbers real quick, and we have, for this, the angular is, make sure I'm putting this in right, it is 120. Multiply that by 2, and then this is 0.5, no, 0.6 kilograms times 1/2, and then d is 0.35 squared. Solve that, and we get 4.41 kilograms per meter squared over seconds. Alrighty, so now we have that. Now we look at our second part, and we see that we're looking for the translational angular momentum. Well, looking at this problem, I noticed that if we look at this axis right here, that the rotation of it is actually going to be the same thing as its translational angular momentum, because as it's rotating right here, that's how much it's actually moving. So I guess it's a little shortcut that I took, but angular momentum of the rotational is going to equal the angular momentum that's translational. So we're going to use the same formula of inertia times omega, but this time the radius is different. The radius is going to be a maximum of b plus 1/2 of d, because this ball, that's the furthest it can be, and the closest it could be is b minus 1/2 d. Alright, and all these are going to be the same as each other as it rotates, because as you take distance away from one, you give it to another, and they'll all equal out to be the same distance total. So we rewrite our inertia as 2mb squared, and then we just have to multiply that by the omega given, which is 140 radians per second, and then we'll have our translational angular momentum. So 0.6 kilograms, and b is 0.525. We'll square that, multiply it, plug it in, and we get 46.3 kilograms times meters squared over seconds. Alright, and the easiest part right here is we have the total, which, simple enough, all we have to do for the total angular momentum is add the rotational and add the translational. So 4.41 plus 46.3, that gives us 50.7, and that is also in kilograms meters squared over seconds. That was sloppy. And also, important thing, direction. Well, I figured I'd talk about direction all at once. We know that the direction of this is going to be in the negative z direction, because of the right hand rule.